Yeah. Hey everybody, thanks for coming. Let's get started. There are two ML talks in parallel, so we're lucky to talk here. So today's topic is multi-runtime serving pipelines. I'm CTO of Hydrosphere.io, and this talk is mostly based on our open source experience and which is in active development right now. And yeah, as a company, we provide solution and open source solutions for deployment, serving, and monitoring machine learning models. So that's an alignment of the topic and our expertise and so on. So I believe it's pretty obvious for everybody that the machine learning project has two major phases. The first one is offline, which happens offline in development, training. And the second one is when you actually push your model into production, and it's somebody calls it deployment, serving, or scoring, or inferencing. So these are basically two fundamentals, phases that we distinguish. And today we're talking about the second one. And when people talk about the model deployment, they usually mean a deployment of just one model. And providing some API to them for scoring, like you deployed a model for image recognition, and you recognize these images. But let's take a look at the real-life use cases when you need more than one model to be deployed in a end-to-end application, artificial intelligence application. In this case, we have a call assistant application when we have it listens to the conference audio, it filters, pre-process, it recognizes speaker, it does some context-aware speech-to-text translation, it extracts knowledge from that text and then provides some action. For example, if it's a sales call, it could provide drive this call and offer a discount. So this is, I'm not providing you a reference architecture for this type of use case, but just to give you an idea what type of meta pipelines I'm talking today. Yeah. Another use case is for example, you are at eBay and you have millions of products, and you would need to match these products for different purposes, for deduplication, for pricing optimization, or any other things. So you would probably have an image model, text model, title model, and maybe other models that will work in ensemble to provide the final result, the final insight to the business users. So this is, again, you will have multiple models working in the same context and in the same pipeline. So that was like my high level context. Let's take a look at the model deployment from the operational perspective. As operations, as software engineers, we see the model artifact that has the following components. First of all, it has the actual model data, the weights and coefficients of that. It has some runtime where the model runs. It might be C++, Scala, Java, whatever. There is a bunch of dependencies from machine learning frameworks like TensorFlow, SparkML, and others. And there is a model that is responsible for API and the infrastructure. So it's, and I would like to highlight a little bit this the importance of API and logistics. You see that a limited set of requirements for this for this component that is extremely important, and it's required when you push your model to production. So it has HTTP, gRPC support. It should provide an API to Kafka or Flink or any other streaming engines to consume messages from them and score it in real time. It should be discovered in your microservices ecosystem as a service, yeah. And there are some bunch of other stuff which is I believe you are all aware about. And the one thing I wanted to highlight as well. So for when we talk about machine learning deployment, the importance and the requirements for the level of requirements for this type of API and logistics is much higher than for ordinary microservices. the reason why. So, for example, when you have an ordinary Java microservice, you might have a variety of unit tests. You might test it in offline, in test environment, and staging, and you could be sure in 99% that it will work well in production. With machine learning model, this is a usual case when the model works differently in offline training set, in production. So the precise monitoring not only of a latency, but the quality of the predictions is extremely important. So you could not physically push the model to production without without covering all these requirements. And this is like the example how the monitoring could be implemented. So we continuously listen to the inputs and outputs of the model, and we do some probably clustering or anomaly detection there to identify different model degradations or data drifts in production. So, for example, like the same model could work well for males and could not work well for females, and this could be discovered right online in production. By having this like smart monitoring in place, we are basically shifting experimentation phase from offline research to real-life production. And if we will multiply these requirements for the API and logistics to the number of runtimes we might have for different machine learning frameworks, we will have like infinity set of different implementations in Flask, Spring Boot, and other frameworks that maybe with something some ad hoc metric systems attached to that. And have you guys attended the Istio workshop yesterday? Does anybody? Okay, I guess for those who attended, you see the really interesting alignment of the problem I'm describing and the story that Envoy and Istio are telling. So, having multiple runtimes with different dependencies, different languages, they require a unified way to provide an API and logistic and routing in production. So that's why we took the Envoy and we attached that as a sidecar to our main application. Main application represents the actual model deployment, and delegated all the API and logistics stuff to the Envoy. So our main model, a Docker container with main model, is really tiny and clean and just provides a business logic and actual serving or inferencing logic. And it doesn't know about the entire world. It knows just about Envoy, which is sitting right behind you. So, as a high-level architecture, I will skip it really quickly. So we strongly believe in function as a service paradigm. So we basically treat a machine learning model as a function, as similar like AWS function. That could be registered in the cloud, and it could be triggered from anywhere of your application. So we have a functions registry, we have a mesh of serving runtimes powered by Envoy, and the integration with infrastructure with CPU, GPU, and Spot instances. So, and where are the actual pipelines? So the models we deployed, the functions we deployed to the cloud, they are actually building blocks for the applications. Yeah, and applications are like virtual public endpoints that for the models or compositions of the models. In that case, it's just for user experience. Let's take a look what we have here for demo. For those of you who are familiar with TensorFlow and the image recognition, we trained SSD single-shot detector model. So it's It's just a state-of-the-art image recognition model and architecture. So we basically just recovered that from checkpoint and saved to the model repository, to the S3 here. And this S3 bucket is mounted as a repository for our ML Lambda, the open source product that we are, which is in active development right now. So we have we could discover a couple of models that are also sit there in that repository. We could just browse their versions, and this is the actual SSD single. Do you guys see what's happening on the screen? Okay, it should be better. So for this case, we have and you can test, deploy the models. When you deploy it, you just provide, you select the actual environment you want to deploy it in, on GPU, on CPU, and runtime that I've talked about. And this particular model has a single shot detector. There is one version which is deployed on GPU, so we can send a pixel there and get a result. Results basically are bounding boxes of the objects detected on that image. So this test doesn't make sense because it's just one empty pixel. And another model is deployed on CPU, on simple CPU, and now we want to build a pipeline. The pipeline has the actual model scoring and post-processing stage. So the pipeline description looks like the following. It's pretty simple. You have a SSD pipeline. You describe the first stage that you wanna route the 50% of your traffic to the model 1, and another 50% of the traffic to the model 2. And these are actually GPU and CPU versions of the same model, but they are just physically deployed in a different runtimes here. And you have the stage 2, the second stage, which is like we call it in this case SSD labeling. It's just post-processing, and it's doing something with a model output here. So, and when we deploy this kind of pipeline, we see it's being displayed here, and now we can send the traffic to that pipeline. So it's to this application. It has a public endpoint, and also we could send the traffic to the Kafka. It's also will be like consuming that traffic from Kafka's, scoring that, executing a pipeline, and sending the prediction results back to the other Kafka topic. So in that notebook, I'm going to. So this is, by the way, the model output. It looks like this. It's a pretty canonical single shot detector model here. So here we have just a while loop, and we are sending like random images to our application, and it started to get scored. Yeah. So you see that new images and new scores appear here, and let's take a look at what happens with the metrics. So as I mentioned, the metrics are really important, and our pipeline should emit as many metrics as possible for monitoring, for tracing. And in this case, for tracing, we have a Zipkin that receives these metrics, and we can observe some latency metrics here. So, and we can trace every request and just browse how long it lives in what stage. So here we have it's 6 seconds. It's obviously a CPU instance, which is slow. It's the same model on a CPU instance, and we can filter by shortest, and this is it's basically scores a GPU instance. It's just below 300 milliseconds. Of course, it's not the state of the art. It's not a performance benchmark. because the model is not highly optimized, but it's just to show the mechanics, how can you deploy the models in different runtimes and build the pipelines from these models. So the couple of follow-up questions I could cover. Yeah. So why not just one big neural network? You probably, everybody is excited about the Google experiments and Google translation. So with an NVIDIA experiments with self-driving cars, when they just trying to train one big neural network. So it's a good research. It's a good cases, but it's not always possible. And often it requires a lot of black art, and there might be, and people usually start with rule-based models, then move to the machine learning models, then then probably merge some stages into end-to-end neural network. And basically every stage of the meta pipeline I just demonstrated to you might be in fact the end-to-end neural network. But the stages could be there might be other stages that are new end-to-end network in their own. So why not just one Python script? Because usually when like data scientists they do a training pipeline, they just write a Python script. It's just ordinary functions, and they just execute it in a chain. And yeah, of course we need a modularity, and stages could be the stages of these pipelines could be developed by different teams, and you can even order a particular voice speech-to-text model from a third-party provider that is that has a niche expertise in that particular case. So, and anyway, you need to assemble. You have to do a little bit plumbing on sticking all these models together. So we need better versioning. We need to version every stage of our pipeline and to track down the changes that are happening in a life. So, and of course, we want to take a lot of some cool stuff from microservices world, like request shadowing, canary testing, and other stuff. You've probably heard there is like TensorFlow serving, and so why we're not using just the TensorFlow serving? So first of all, there are other machine learning frameworks rather than TensorFlow serving. You might use deep learning for J, you might use scikit-learn, and actually the data scientists, they tend to experiment with a new framework every day, and you could not just limit them to use one JVM-based or TensorFlow-based models. So in order to provide a freedom, it would be great to support as many frameworks as possible. And we need better versioning if we will dig deeper into TensorFlow serving. They kind of reinvent versioning. We like have a Docker per version, and it provides more natural way to version your models, and it provides better immutability of your models. In TensorFlow serving, where you have to, it acts as a load balancer. It reinvents load balancing and reinvents versioning. And this already exists in other world. So we want to utilize the best practices from the rest of the world rather than following TensorFlow serving paradigm. And we don't want to deal with state, for example, when in TensorFlow serving, when you have a model version the first version of your model, and you want to load the second version of your model, you have that intermediate state that, okay, the model is not being loaded yet, that it's not ready to receive a request from the outside of the world. You have some logs and mutexes there. So we don't need to deal with that if we have a Docker per image per version per model version, and we just scale it horizontally with all the cool frameworks we have in place. Actually that's it. I'm done. I have just 1 minute or 30 seconds for questions. I apologize. Probably after the previous talk that introduced you to deep learning, it might be a little bit advanced. That after introduction, we jumped right into production. So please.
If there are any questions? Okay.
Yeah.
Well,
thank you, guys.
Thank you.